Welcome back. Okay, so this is, I think, the third lecture in this series on complex analysis. We have introduced what we mean by a complex number, a number with a real and an imaginary part. We have started to talk about complex variables, this variable z equals x plus iy. And now I want to talk about functions of a complex variable, functions of z. Just like we have normal real-valued functions, cosine of x, sine of x, e to the x, logarithm of x, we're going to have functions of this complex variable. So their inputs will be complex numbers, and their outputs will be complex numbers. And we want to think about functions of z so that we can think about doing calculus on these functions. These functions are going to end up being the solutions of our ordinary and partial differential equations. They are going to be functions that represent things like the wave equation in quantum mechanics and things like that. So they're going to have very real interpretations in physics. And so I need to introduce what are the properties of these functions, what do these functions look like, what are the things that are the same about these functions that are similar to real valued functions, and what is different, what's weird about these functions. Okay, so that's what we're going to talk about now. Probably the one I like to introduce the first are these kind of power functions, so powers of a complex variable z. So z to the n is a function of z. Just like a real valued x squared, you can have z squared. And this is going to equal r times cosine theta plus I sine theta quantity to the nth power. And so sometimes I'm going to use the polar form of the complex variable z in terms of its radius and its phase angle. So maybe I'll just draw a little picture here. If this is the real value of z and this is the imaginary value of z, then my little z value here can be written in terms of r and theta, a radius and a theta in this two-dimensional complex plane, or it can be represented in terms of the real part x and the imaginary part y. So you can say z equals x plus iy, x plus iy, or it can be written in terms of r, its radius, inclined at an angle theta. And so here I usually like the polar form when I'm doing things like multiplying, because it's easier to take powers in polar form. Good. So I'll just label these as I go. This is kind of the power function, where I literally just take the power of z. And we're eventually going to build up to the Taylor series. We can do full Taylor series expansions, things like e to the z, sine of z, cosine of z in terms of their Taylor series. But we're going to start with just finite powers. That's a totally valid function. Another function that's interesting would be a power series. Maybe I'll alternate colors here. So a power series would be something like a sum from k equals 0 to n of some coefficient ak times z to the power k. So if this is a function, if z squared and z cubed and z to the fourth are functions, then I can add up those functions with some complex coefficient ak. So these are, what are we going to call these? We're going to call these power series. Okay, power series. I can also do things like create a rational function. I could say that, and I should probably call these f of z's. I should probably say that this is, f of z equals, f of z equals, and then, I can do other things like I can have f of z equals a rational function, basically a ratio of two different power series, k equals 0 to n times ak z to the k, divided by the sum, let's say, of j equals 0 to m. These don't have to have the same order. B subscript j to the z to the j power. z to the j power. Okay, so this is a rational function. Again, just like I can have a rational function of x, a real valued rational function, I can have a rational function of z. This is a rational function. I'm going to start getting into the exotic ones in a minute, sines and cosines, logarithms, hyperbolic sines, hyperbolic cosines, exponentials, things like that. The last one I want to introduce is the Taylor series, right, which is essentially a power, this power series where now n goes to infinity. So now I'm going to have f of z or z equals the sum from k equals 0 to infinity of a k. And here I'm going to also make it so that it's a little more general. It doesn't have to be Maclaurin series where it's expanded about z equals 0. We're going to say that this is z minus some z naught to the power k. So this could be centered at any point z naught, and I'm going to take an infinite sum of powers of z expanded about that point. And just like in real valued functions, this is our Taylor series. Good. Okay. And so some of these functions are better behaved than others. So these power functions, just z to the 2, z to the 3, z to the 4, those are very well behaved functions. They are continuous and smooth everywhere. The notion of a derivative makes sense. You can do calculus on these. These are called analytic functions, and they have really, really nice properties. The sums of these, the finite sums, these power series are also really nice quantities, really well-defined, smooth functions. These expansions here, if this converges, if this has a convergent Taylor series, then these are also really nicely defined analytic functions. So functions like e to the z, cosine of z, sine of z are going to be nicely defined convergent Taylor series. And so what I mean by that is the Taylor series is convergent. The Taylor series is kind of well defined if is only convergent, and this is just like in real value calculus. Remember, you write down a Taylor series and you see, does this infinite sum actually add up to something that's a finite number? And for what values of z is it convergent? So this Taylor series is only convergent if this limit, L equals the limit as k goes to infinity of ak plus 1 divided by ak. And these are complex numbers, so I'm just going to take the ratio and then take the kind of radius or the norm of those if this exists. And then we would say then f converges for z minus z naught, for a radius around that z naught less than 1 over L. This is the radius of convergence. So essentially there would be, some z naught, and there's some radius here, which is, 1 over L, where L is this limit. So if I am within a radius of convergence where this Taylor series converges, where this property is true, then this Taylor series converges anywhere within that radius, okay? And again, what that means is that my function is smooth, continuously differentiable. I can take derivatives of this function, and it's a so-called nice analytic function in that radius of convergence. So I'm going to have a whole video on what it means to be an analytic function. These are super, super important functions that essentially are the solution of Laplace's equation from partial differential equations. And it's a really, really special and important class of complex functions that have convergent Taylor series, okay? And if the Taylor series converges everywhere, we would say that it is an entire function, like it's entirely convergent. This is just nomenclature complex analysts use. Good. Okay, so I want to give you an example of how we would compute a convergent Taylor series and how we would kind of run this test. Just like we would run this test in a calculus class, I'm going to show you how to do it for complex functions too. So I think the easiest complex function to try this out on would be the complex exponential function. So let's try this. Let's try the exponential function. exponential. And the exponential function is e to the z equals, I wrote this down in the last lecture, this equals the sum from k equals 0 to infinity of z to the power k divided by, k factorial. This is a k factorial. And so that a k coefficient is 1 over k factorial. This means essentially that a k equals 1 over k factorial. That's the coefficient out front of this. And so what we want to do to check the convergence, so we're going to check L equals this limit. Sorry, my pen is squeaky. I know that drives some of you crazy. Of k goes to infinity of ak plus 1 divided by ak. Okay, and I got to be really, really careful. Ak plus 1 is 1 over k plus 1 factorial. That's ak plus 1 times k factorial. That's 1 over ak. 1 over ak is k factorial. And that equals, so 1 over k plus 1 factorial times k factorial. All of the k factorial inside of here cancel out. Remember, k factorial is k times k minus 1 times k minus 2 times dot 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 times 3 times 2 times 1. So k plus 1 factorial is just k factorial times another k plus 1. So the first k factorial cancel out, and I just get 1 over k plus 1. I don't need the absolute value anymore, but I'll keep it. And we're taking the limit as k goes to infinity. And the limit as k goes to infinity of 1 over k is 0. So essentially, this L, this Taylor series is only convergent if this L exists. If it's bounded, it definitely exists. It's the number 0. And F converges for everything within a radius of 1 over that number L. And kind of 1 over 0 is infinity. So the radius, the radius of convergence is infinite. That means that this exponential function, its Taylor series, converges everywhere. For every single z, you can write down in the complex plane a bajillion, like 5 million plus 10 billion I, that will have a convergent e to that number. If z equals 5,000 plus 9,000 I, e to that number exists because this has an infinite radius of convergence. For every z in the complex plane, e to the z is a well-defined quantity. So that's just one example of a function that has a well-defined radius of convergence, which means it has a convergent Taylor series, which means it is analytic everywhere. Again, I'm just going to spit out all of these words because your complex analysis teacher is probably using these words all the time too. And because this is analytic everywhere and has a convergent Taylor series, that means it's an entire function. This function is called entire. Let's write it. This is an entire function. Okay, good. Good. Okay, so those are just some functions that we use all of the time. Things like, z squared, z cubed, z to the fourth. A sum of those polynomials. An infinite sum of those polynomials if that Taylor series converges, like it does for the exponential function. For sine of z, cosine of z, we'll show that those also converge. Hyperbolic sine, hyperbolic cosine, things like those. Good. Maybe I will give a few more just interesting facts here. So I'm going to revisit the power function. So we're going to revisit z to the n here. And remember, when we have z equals, I'm essentially going to recopy this here. It equals r cosine of theta plus I sine of theta. And that means that this is r e to the I theta by Euler's formula. Euler's formula allows me to take e to the I theta and write it as cosine theta plus I sine theta. That was the last lecture. And so that means that z to the nth power is just r to the n e to the I and theta, okay? And we already wrote this down in the last lecture. This is de Moivre's formula here. So this is r to the n times cosine n theta plus I sine n theta. The reason I'm rewriting this here is because I want to show you kind of in a picture what this looks like. So if I have my complex plane where this is real and this is imaginary, this is my complex plane, then if I have some z variable that is, let's say here we have z equals r e to the I theta, it has some length, and it has some, let's say some theta and some radius. Then if I look at z squared, I am going to square the radius and double the angle. So it's really easy to take powers in the complex plane when you think about them in polar coordinates. So z squared, let's see if I can actually draw this. Z squared is going to equal r squared e to the I 2 theta. So this is 2 theta, and this is r squared. And similarly, r cubed, z cubed is, it's going to be a little hard to write this, r cubed e to the I 3 theta. So this is going to have r cubed as the radius, and the angle is going to be 3 theta. And you're seeing that I'm having a hard time drawing perfectly this angle, which is 3 theta, but you can take my word for it, that's what you would get. Okay, so these functions here are really easy to understand, again, when you think about them in polar coordinates, because the radius gets, taken to that power. So z to the n has radius to the n, and its angle, its kind of phase angle in the complex plane is multiplied by n of that z variable. Good. Okay, what else do I want to show you? There's probably a few more things. We're getting close to finished. There is a super, super, super important function, the complex logarithm. So the complex exponential is really easy to understand. It's exactly like the real valued exponential. It just has this convergent Taylor series, except now instead of plugging in real numbers for z, I can plug in any complex number I like, and it converges everywhere. There is the analog of the complex logarithm. The complex logarithm is a little bit more exotic, and in fact, it's such an important function, and it's so kind of interesting and strange. I'm going to have a whole lecture on the complex logarithm. So log of z, you're going to have to stay tuned, okay? This is the next lecture is going to be all about the log of z. But I'll tell you about a couple more fun functions that I think about a lot. One would be the trigonometric functions. So our trig functions are things like sine of z and cosine of z. And so these sine of z and cosine of z, there's lots and lots of ways of defining them. I could define them using the Taylor series, like I could take the real valued Taylor series of sine of x, and I could replace x with the complex variable z, and that would be one fine definition of sine. I would have to check that it has a convergent Taylor series everywhere. That's easy to do. That's a good homework problem for you. And at least the first part of what the Taylor series is, we covered in the last lecture. But another way to write this, which I think is kind of nice, is in terms of these complex exponentials. So sine of z is e to the I z minus e to the minus I z divided by 2I. So you can confirm that if you take the Taylor series e to the iz and the Taylor series e to the minus iz and you subtract them, all of the even terms will cancel out and you'll only be left with the odd terms. And if you divide by 2I, you'll be left with the Taylor series for sine of z. Similarly, for cosine of z, this is, I'm assuming you add these. I'm not even going to look at my notes, because that kind of has to be true. If this kills all the even terms, this will keep all of the even terms. And instead of dividing by 2i, ooh, I can't remember if this is divided by 2i or 2. 2? ? question mark? Okay, so there are these formulas though. Essentially your trig functions also can be expressed in terms of these exponentials. You can sum them up. Please verify this is a really good homework problem for you at home. I think this is a 2. It might be a 2i. You should check that. I'm pretty sure this is a 2. I'm going to go ahead and assume that this is a 2 because the i's probably have already canceled out. But I would like you to verify this property at home. And so just like e to the z has a convergent Taylor series everywhere, you should also confirm for yourself what these Taylor series expansions are for sine and cosine of z, and go through the check to confirm that their radius of convergence is infinite. That's super important. We also have hyperbolic functions. We have, for example, sinh, the hyperbolic sine of z, is equal to e to the z minus e to the minus z divided by 2. Hyperbolic cosh, this is the hyperbolic cosine or cosh function, is again e to the z plus e to the minus z divided by 2. And again, I'm pretty sure these are actually real valued 2's, but you should just double, triple check that there's not an I in this denominator. You could define the tangent function and the hyperbolic tangent function the same way, and you should check where those are or are not convergent power series. A couple of good identities I think you should know, just while we're at it, are things like I times sine of z equals sinh of iz. Again, that's really, really easy to verify here. You should just verify that I times sine of z equals sinh of iz. Similarly, cosine of z is equal to cosh of iz. Again, this is kind of like because of even and odd functions. Remember, if I take sine of negative x, it's equal to negative sine of x, but cosine of negative x equals just regular cosine of x. This is a very similar property, but with the imaginary number. And so on and so forth. You can verify more of these things like sine of iz equals I times sinh of z, and so forth. Cosine, let's say cosine of iz equals cosh of z, and then things like e to the z equals cosh z plus sinh z, and e to the z equals cos iz plus minus I sine of z. This is a minus right here, so this is a minus. Okay, and these are all things that if you were taking a complex function class, like if you were taking a whole class on complex analysis, this would be like homework 1. Verify all of these different relationships. Check that the Taylor series is convergent everywhere. Find out and derive all of these identities just so you're really, really good at manipulating these. Again, it's good to be able to manipulate these quantities, these exponentials, these sines and cosines, and so on and so forth, because these are going to end up being the solutions of our partial differential equations. For example, sines and cosines and sinh and coshes come up all the time in the heat equation. If I want to find the steady state heat distribution in a rectangular metal plate, I'm going to get sines and sinh and cosines and coshes all over the place. So it's really good to be able to flexibly go back and forth between these quantities. Okay, good. So this is just a small subset of the many, many, many functions of a complex variable. Things like powers of that variable, z squared, z cubed, z to the fourth, finite expansions or infinite Taylor series expansions of those powers, which we hope are convergent everywhere, like the exponential and the sine and the cosine functions. If they are convergent, if your function has a convergent Taylor series, it's called an analytic function, and its real and imaginary parts solve Laplace's equation. I'll have a whole lecture on that coming up. And then soon, I think in the next lecture, I'm going to tell you about this really, really interesting function log of z, which is analytic most places, but not at the origin z equals 0. So this is a kind of an exotic function, but it's a good example of some of the weird things that can happen in the complex plane. OK, that's all coming up. Stay tuned. Thank you.